Okay, well, congratulations. You now have all your digital I/O hooked up correctly. You have your analog I/O connected, or at least the input. We'll do the output later. And hopefully you've got it to where you have a basic program that I gave you running that's verifying all the digital and analog. So right now I have the just basic digital test program running in the PLC. So you can see it's flashing all of my lamps based on T3. Same thing we've done before, motor on T2. What we're going to talk about now is how can we use that analog input that by rotating the potentiometer, we're varying a signal nominally 0 to 10 volts. And from our previous video, you saw that in the actual input value, that ended up ranging from 0 to somewhere a little over 60,000. So that's great. We now have a way to have a variable number based on a physical change out here. That's the function of an analog input. In this case, it's just position that we're measuring, right, by rotating the knob. A more typical application would be that analog sensor would be maybe measuring the pressure of a gas or measuring the temperature of a process. But for our demonstration, we're representing the position of this potentiometer. But let's say we wanted to use that to vary the time of the flashing lights like I used in that example program. Our on-off time in that case was in the range of maybe 100 milliseconds up to 1,000 milliseconds. So how do I take my 0 to 60,000 number and get it into useful units like milliseconds or percent speed or RPM, something like that? So there's a number of ways we can do that. We can do it with just basic math instructions. So let's say I wanted to take that 60,000 maximum value and turn it to 100. So I wanted to rotating my knob, change a variable from 0 to 100 instead of 0 to 60,000. That's a pretty simple case, right? We could do that just using basic math instructions. We could do a divide. So let's take a look at that. If I go and look at my global variables, you'll see my analog input 1 right here. That's the one connected to my potentiometer. So when I have it all the way to the right, it looks like it's bouncing around 0 to, pretty low down there. And then all the way to the left, I go up to, looks like 60,970 maybe would be an average high there. So if I want to end up with 100, I can just figure out the multiply or divide to get down to 100. So let's do that using a basic math instruction. So I have just an empty program in here, and we haven't really had multiple programs running before. We did talk about this back in MEC 231, that in Connected Components Workbench, the programs basically just execute in order. We don't write instructions that jump between different programs or call different programs, but it can be a way for you to just kind of group your code logically. So I have the digital I/O program here that's running that you've seen before just to test all the lamps and switches. But now I've added another program just to keep separate the instructions that we're using to demonstrate manipulating analog variables, just so we don't have all those extra rungs in here. Okay, so I will disconnect so we can do some editing. And we said we wanted to go from 60,000, let's see, turn on my calculator, 60,970 roughly, to 100. So to do that, you figure out what am I going to need to divide 60,970 by to get 100. So if we do that on a piece of paper, say x times 60,970 equals 100. So then x, the multiplier or divider that I'm going to need, in this case if I'm doing times, we'll get multiply, it's going to be 100 divided by that. So that, oops, sorry. That is 1.64015 times 10 to the negative third. That's one way to do it. Or if I wanted to divide instead, that might be easier. Just do the inverse of that. That answer is obviously 6 609.7. So that's probably an easier way for us to do it, is just to divide by that number rather than multiply by this number. So let's do a couple things. Let's create a variable first. Let's create a variable. I'll get rid of all of these ones that we're not using now. Oh, yeah, I guess, sorry, those are the variables for the other program. Local variables, there we go. Okay, so let's create a real variable that's going to be our divider. And it has to be real because it had a decimal point there of 609.7. So let's see, real. And I'm just going to put 609.7 in as the initial value so I don't have to set it. Remember, you could just use a move inside your program to move in 609.7. Okay, so I now have the divider, and then let's have a scaled output. Scaled out that will also be a real number. And we'll use that for the result of our division. So go back to our program. And let's add a divide instruction. So divide, and I'm going to divide our analog input value. So if I come to my I/O and look for analog input 1 and divide it by my divider and put it into my output. Okay, so let's just test that much and see what happens to that variable if we download that. Oh, I think I had I forgot to change it to real. So I'm glad that happened. Again, as an example, I always need to be checking my data types. So you can see it was looking for, let me go back to the program so we can see it here. This is an unsigned integer, the input from the analog, and I was dividing it by a real. So I need to match my data types. I could divide an unsigned integer by another unsigned integer, but I can't mix the data types. There's no decimal point related to this input here. So I need to change my data type. So we do that using any to real would probably be the easiest way. So I'm going to take any to real, and I'm going to take that analog input, which you can see here, it's an unsigned integer, and I'm going to move it into a new variable that I'll have to create called analog. Let's just call it analog real. So that will be a real value that's identical to the analog input. So it'll still go up to 65 or 60,970. It's not doing any scaling here. It's just changing the data type from unsigned integer to a real. And so here I'll switch that to my real variable. Analog real. Okay, now let's try building that. Okay, that built fine, so let's download it. Okay, and if we go look at our variables now, once it gets online here, you can see right now the input is at 60,970 roughly. That's an unsigned integer. You can see there's no decimal point on the actual input itself. And then our any to real is just taking that number and basically adding a 0.0 onto the end of it, turning it into a real number. Then our next line is dividing that real number by another real number, 609.7, to get us our scaled output, which again is a real number. And you can see it's pretty much right up at 100. So this was an easy way to take our 0 to 60,970 and turn it into a 0 to 100. So let me rotate the potentiometer, and you can see our scaled output is decreasing down to 0, bouncing around right at the bottom of 0. So that would be an easy way to turn this 0 to 100. But it gets more complicated if I want to go, instead of from 0 to 60,000, what if I wanted to change from like, let's say I'm adjusting the speed of a motor. And so I want that 0 to 60,000, 0 to 60,970 to instead be like 30 RPM to 45 RPM. So I'm changing both the total range of the value. I'm changing the low end, the low threshold. Instead of being 0, I want it to be, say, 30 RPM. And I want to adjust the top range to be 45 instead of 60,970. You can totally do that with math instructions. It just takes a lot more math instructions, right? You have to create an offset so that you're not at 0 for your low end anymore. You need to have a scaling factor, and then also a divisor like we did here to limit your top end output at 45. So very doable, but we don't have to do it in this case because there's a built-in instruction that allows us to do that. So I'm going to disconnect so we can edit, and I will get rid of these rungs and show you one built-in instruction that lets you do pretty much everything we just did plus a lot more. So if you type in scale, you'll see scaler, and this is a really powerful instruction that's really handy to use. Okay, so let's get the user manual up, and I think I'm on scaler here. Yeah, so here is the reference manual, the Micro 800 reference manual, our programming guide basically, and here is the table that's most useful that tells us what each of our parameters for this instruction are. So the enable, just like we always have on all rung and ladder diagram instructions, that's just whether it's going to do the instruction. Then we bring in our input number. So this would be the value that we want to scale to a different range. Important to note here that the input is not limited by input in and input max. It'll allow values other than what we put in down here as inputs. This is input min and input max are just what it's going to base its math upon. So if you actually wanted to not allow it to see a value less than what you put in here, there's other instructions called limit alarm that you can do to kind of constrain your variable to never go below a certain value or above another value. And I encourage you to go take a look at that instruction as well. But right now we're going to talk about scalar. So, and we'll do an example, a number of examples here that help us understand what's going on here. But basically, input is our actual number that's changing. So in this case, that would be our analog input. And you can see here the format is real. So our analog input is actually an unsigned integer right now. So we know that we're still going to need our any to real conversion before we get to the scalar. And then all the other variables that we'll use within it are going to be reals as well. So the input minimum is what we want to consider our low end of the range. So for us, our input variable is going between 0 and roughly 60,970. So for starting, I would say my input min is going to be 0 and my input max will say 60,970. So that's just telling it, okay, what is my variable going to range from in my input side? And then the powerful part of this program is now the output min and output max. This is where I can put in, let's use the example where I said I want it to range from 30 RPM to 45 RPM. All I have to do is type in 35 for my output min and 45 for my output max. So let's go do that right now with that instruction. So I said I need to add an any to real. And we're looking at our analog input, number 1, and I'm going to use that same variable that I already created called analog real. Okay, and then analog real will be our input. And I'm going to put in just values for input min and max. Again, those could be variables or parameters that I programmatically changed. It doesn't have to be a fixed number, but for now I'm going to do that. So I'm going to say 0, And just watch, if I just put in 0 with no decimal point, it's going to give me an error because again it's expecting a real. So I have to put in 0.0 for it to consider that. In input max, I'm going to put 60,970, I think is what we decided, and again 0.0. And then my output min, I want to be 30 RPM, I said. And my max, I'll say 45 RPM, again with decimal points. And then my output, let's see, I've got scaled out, I'll use that again. Okay, let's build that. Looks good, and go ahead and download it. Okay, so you can see right now on my scaled output, I'm at 30 with it all the way to the right. And if I rotate to the left all the way, my output's 44.999. So you can see I didn't go through all the math instructions you would have to do an offset in both input and output. From 0 to 30 and from 60,970 to 45. But you can see in this one instruction it has done all of that. But here's another nice thing, great thing that saves you more math instructions. Right now it's 45 RPM with the knob all the way to the left, and it's 30 with it all the way to the right. So that's kind of the opposite of how we typically expect things to behave, right? We often, just by tradition, expect an increase to be a clockwise motion. So if instead of going from left to right or clockwise to decrease, if I want to do what we'd more expect clockwise to increase, it's really easy to do that with the scalar instruction too. I would just switch my ranges here. So I would do 45.0 and 30.0. And that's another one where you're saving a lot of math by having that built into there. Okay, so now you can see my output scale is now 45 with it all the way to the right, and 30 with it all the way to the left. So I've just inverted my scale just by swapping those two variables. And again, we didn't go through how you would do that manually with arithmetic instructions, but believe me, this is a great time saver having this. Okay, I think that's a good first introduction to scalar. Go ahead and practice this. I'd like you at this point to write a program like this, basically just 2 rungs, and practice scaling your analog input. Let's say we want to scale it to be, let's say it was a conveyor and we wanted to do it in feet per minute. So with the potentiometer rotated all the way counterclockwise, so pointer to the left, let's say we want to have your output variable be 10 feet per minute, or 10 feet per second, I guess would be, well, yeah, let's say 10 feet per second for whatever we're controlling with it all the way to the left. And then it varies up to, let's say, 25 feet per second with it all the way to the right. So go ahead and write out a program that you end up with a 10 to 25 range from your potentiometer. Okay, so I trust you were able to get that working. It's pretty simple, right? 2 rungs. Basically just converting our input to real and then using the scalar instruction. Here you would have had 10 and 25 for that. So let's try another just hypothetical to kind of see how we could use some programming to change these instead of just using hard-coded. So let's say now instead of having a fixed output range of 10 to 25 like you just did, or 30 to 45 like I have here, let's say instead we want to use this potentiometer to control the speed of something, but we want to have 2 modes. Basically, we might have a fine control mode where we want the motor to be running real slow, like let's say maybe between 0 and 5 RPM, and we could use that to adjust to kind of creep up to an initialization point. So let's say we have a toggle switch that controls whether we're in the fine control mode or the speed mode. So with the toggle in one position, we want our speed to be, let's say, 0 to 5 RPM. And then when the toggle's in the other position, we want the potentiometer to be adjusting kind of our main running speed. And let's say maybe in that case it's between 30 and 40 RPM. So we have two different speed ranges, one potentiometer, and we want to be able to switch back and forth between those. So not a whole lot more involved there, but a little bit. So now we're going to need to be looking at our toggle switches. So in this case we'll use toggle 3 because it is a just, two position. So we'll say when toggle 1 is up, we're in our fast mode, and when toggle 1 is down, we're in our slow mode. So let's take a look at toggle 3. Sorry. Toggle 3 is our 2 position. So when it's in the up position, I think I said we want that to be, let's see, I said that was the fast mode, I think. So we'll say control a just Boolean bit that we'll call fast mode. And so we know that if toggle 3 is not in the, so we don't even need to add another bit for the slow mode because toggle 3 is only in 2 different positions, right? One is either up, in which case we'll be in fast mode, and then if we're not in fast mode, we know we're in the fine position mode. Okay, so now we are going to have some variables that we're going to move into our output range, and I hope that's clear. Our input range is not going to be changing in this example, right? That's set by the voltage signal coming into our card. So our range is 0 to 60,970. That doesn't change depending on what application we're using here. The only reason that would change is if we maybe swapped out our potentiometer or had a different resistor in there. If you think back to when we were talking about analog, this input max, if we were going all the way up to 10 volts, it would be up at 65,536 roughly. But since our voltage range is only 0 to about 9.4, our max is 60,970, and we're taking care of that right there. So we're not going to mess with those unless something changes about our hardware input. We're mainly dealing with the output variables. So let's go back to our variables for this, and let's create one that we're going to call, and these will be reals again because we're using them in the scalar instruction. Let's call this fast mode minimum. Okay, and then oops, I wanted that to be a real. And I'm going to say it has an initial value of 0.0. Oh no, fast mode, we said, I can't remember what we said, but we're going to use the range, let's say 30 to 40 RPM. So I'll say 30.0 is my minimum scaled output when I'm in the fast mode. And then we'll say fast mode max. Again, it's a real. And let's say that one's 40 RPM. And then we will have, let's just call it slow mode min. And slow mode max. And that was 5. So we have our 2 ranges. When we're in slow mode, it'll be 0 to 5, and when we're in fast mode, it'll be 30 to 40. And again, I could change those programmatically in my ladder, but these are the initial values I'm going to start with. Let's go back to our program. And so when I'm in fast mode, I'm going to do let's get rid of these. Oh, that one can stay. We're getting rid of our hard-coded variables. And then actually I should create 2 more variables that I'm going to say are current, min as a real, and current max. And let's say we always want to start up in our slow mode. So I'll just put in initial values that match our slow mode values. If I wanted to start up in some different range, I could put those in here, or again do it programmatically inside the logic. Okay, so come back to my program. So I will now add a bit here that says if I'm in fast mode, I want to, oops, I go back there. Wanted that on its own rung. Okay, if I'm in fast mode, then I'm going to move, and I will move my fast mode min into the current min, and at the same time I will move fast mode max into current max. So that's just moving the fast mode variables into there, and then I would want to make sure I have current min and current max in here. So now I can programmatically change those using those variables. Okay, in the opposite case, when I'm not in fast mode, so then I want to actually, I'm just going to copy that. And make that slow mode instead. Slow mode min. And copy that one. And then slow mode max to current max. Okay, let's walk through those real quick. Make sure so our first rung scales our unsigned integer analog input into analog real. We then have our toggle switch that we're looking at. When the toggle switch is in the up position, we'll be in fast mode. That will make rung 3 true, which will move our fast mode min and max into current min and max. In the opposite case, when T3 is not up, then rung 4 will be true, and we would move our slow mode min to current min and slow mode max to current max. Then our scaler is looking at our same input min and max as before, but now the range that it's scaling it to on the output is dependent on what's in current min or current max, and it's still putting it to the scaled out. So I'll build that, make sure I didn't make any mistakes in variable types or whatnot. Looks good, so let's go ahead and download it. Okay, so I'm running now, and my toggle switch is in the down position, so that would be our slow mode. So in that case, when I'm rotated all the way clockwise, I should be at about 5, and it looks like I'm at 4.99, but I'm rotated all the way clockwise, so I have my orientation backwards. So my scaling's fine, right? I'm going 0 to 5 basically, but I forgot about the fact that the number's increasing on our analog input as I rotate counterclockwise, and I want my output range to be increasing as I go clockwise. So I'll need to change that, flip my basically current min and current max to reverse the direction of that. But let's check about the other switching between modes. So right now I'm scaling between 0 to 5, which is good for our slow mode. If I toggle switch up, you can see it jumped from 5 to 40, the scaled output here. So my range is now between 30 and 40, but again my orientation or my positive direction is flipped. So I'm going to disconnect, and we can just edit that by switching these, right? So I'll put current max there and current min here, and that should swap. Okay, and I'll download it again. Okay, so I'm in fast mode still. My toggle switch is up. And now it looks like the orientation, the direction is correct because I have the potentiometer all the way clockwise and I'm at 40. Scroll all the way the other way and I'm at 30. If I go into slow mode, my output is 0 with it all the way counterclockwise, and it is at 5 all the way to the right. So the next thing I want to talk about is kind of limiting the output value to make sure it stays within a range we expect. Let's say, for example, instead of measuring a 0 to 10 volt signal, which is the full range of our card, let's say the sensor we were measuring was a 0 to 5 volt signal instead of 0 to 10. So we were only going to be using about half the range of the card. We would want to set the input max then to, let's say, around 30,000. And we'll go ahead and put that in there as a variable. So, and let's say, get that back to 0. Oops, 0.0. So now our range is roughly 0 to a little less than 5 volts. And that way our output scale is maximized to that 0 to 5 volt input. And that works fine. But what if then something happens to that input variable, the voltage supply gets increased or whatnot, and all of a sudden instead of going 0 to 5, it goes 0 to 7 or something. Our output our scaled output then would go up by a factor equivalent to 7.5 divided by 5, right? And that might not be safe if it is controlling the speed of a motor or the pressure of a tank, something like that. So we often want to limit our output to be what we expect, so that if there's something unexpected happens to the input, somebody miswires a signal so that instead of 0 to 5, it's on a 0 to 10, I guess that's a good example. So let's say it was set up for a 0 to 5 volt signal, but somebody accidentally wired it to a 0 to 10 volt output. In that case, our output would be double what we expected. So you can imagine if you were controlling the pressure in something or the speed of something, it wouldn't be safe in most cases for the output to double. So what we want to do then is a little bit of evaluation and math for the output. So let's say here I'm going to fake that example of doubling my input by limiting my range to 0 to 30,000. So before, my maximum output was based on a maximum input of 60,000 plus. Now it's going to be 30,000. So if before my range was, and to just demonstrate this, I'm going to get rid of the logic. So I'm just going to put in 0 and 10 to demonstrate this function. So right now, for a 0 to 5 volts, which is basically 0 to 30,000, I expect 0 to 10, and that's fine. I'm going to get 10 out when I get 30,000 in. But let's say instead somebody wired it up to a 0 to 60,000 input, which is what we actually have. Well, let's watch what happens to our output in that case. So let's go ahead and download that. Okay, so you can see now that even though I wanted a 0 to 10 output, since my input range is almost twice what I expected it to be, my output is as well. So in this case, my speed would be twice what I expected the max speed to be, or my pressure would be. So that's not a safe condition. So we want to limit that output to be what we expect. And there's actually a limit alarm instruction that can look out and give you an alarm if something goes above it, but I don't want it to even allow it to go above. So in that case, what we do is some math looking at the instruction itself. So I'm going to add a rung down below this that has a compare instruction. So if you remember back to these compare instructions here, I'm going to say if the value is greater than or equal to, and I'm going to look at, remember here, let's go to the manual for those just to refresh ourselves, greater. So here's the greater than or equal to instruction, and it's comparing true if I1 is greater than or equal to I2. So I2 is the one we're comparing against. So I'm going to say if my scaled output is greater than 10, because that's what I want my max to be, even if it's trying to scale it greater than that. So I'm going to say if scaled out is greater than or equal to 10, then I'm going to just move the value 10 into scaled output. So basically, even if it goes above 10, it just keeps resetting it back to 10. So let's go ahead and download that. So you can see scaled output is 10 there. And let's go back to the program. It's interesting, it's not showing me my values as if it's not online. Scroll. Let's go back and look at. So I'm not sure why something's screwed up in my communication there, but if we're watching the scaled output here, I'm at 0, and as I scroll up, I'm getting to 10, about half range on my pot, which is what I would expect because I said my value should go up to 30,000 max. Instead, I'm going to up to 60, but you can see once I hit that 30,000 value, the scaled output stopped increasing at 10 because I have that instruction in there that's watching it. So see here, as this analog reel creeps up to 30, right when I get to 30,000, I hit my expected of 10, but then even though the analog reel continues increasing, my actual output is held at 10. So that's a way to just kind of programmatically ensure that you don't get values you don't expect. So the last example I want to use to kind of introduce you to the scalar instruction is to demonstrate that we can get an output from the scalar instruction that has a negative value as well. So far I've been scaling my unsigned integer input. So unsigned means there can't be a negative, right? It's just 0 to 65,000, and in our case our top end's around 60,900. And so far my output I've also kept only positive, ranging from 0 to 10 or 0 to 100, depending on what scale I've been looking for. But let's say I have a process that runs at 60 feet per second, and I want to use my potentiometer to adjust that down to maybe 55 or up to 65. So I could do that still using only positive numbers by setting my line speed to be at 55 feet per second and then adding up to 10. But in some instances it might make more sense to have your set speed be the mid-range and adjust up and down. And that's what I want to demonstrate here. So I'm going to set my output minimum to be a negative 5.0 and my output maximum to be 5.0. So now it's scaling my positive 0 to 61,000 basically to negative 5 to 5. And so I'm going to want to add a variable. Let's add a real variable that we'll call base speed. And make it a real as well, since we're going to be adjusting it with a real. And let's say we want it to be, I said it's 60 feet per second is our base speed. And then let's add another one that we call adjusted speed. Again, a real. And I won't have any initial value in there for it. Okay, so let's go back to our program. And we now have our scaled output that we'll use to adjust our base speed. So I am going to do a math instruction that adds our base speed to our scaled out, which is going to, so the base speed will be 60 feet per second, and then I'm going to add whatever my scaled output is, whether it's negative or positive, and I'm going to put that into my adjusted speed. So we would expect that to be ranging now from between 55 and 65 depending on the potentiometer location. So let's go ahead and build that, make sure it looks okay. Build looks fine, so I'll download it. Okay, so you can see right now my base speed is 60. My scaled output is about 1.8. As I'm scrolling up again, so I'm going between about 55 and 65 to the other direction. So that's just an example of how I don't have to only have positive values coming out of a scalar input. It's just a super flexible instruction that you can use to adjust numbers just about any way you'd want from one range to another. Okay, I think that's enough examples of using that instruction. Go ahead and complete the assignment given in the instructions about how you're going to vary the on and off times of your lamps using these scalar instructions. Just one hint as a reminder, the scalar instruction is working with real numbers. And when you're dealing with timers, you need to use a time format. So you can do all your adjustment of numbers using real, but in one step you're going to need to do, similar to we did up here, any to real, you're going to also need to use any to time to take your adjusted number back into a time format to use in your instructions.